Hello everyone. In this video, I'll be discussing the solution to the question that was posted on Google group VLSI Design Flow. So the question was related to race in Verilog simulation. So first let us look at the question. So in this question, the this Verilog code was given and it was asked that we should predict the output of this code. So in this code, we see that there is a wire P which is assigned the value of the register Q, right? And there is an initial block in which Q is assigned 1, and then after 5 time unit delay, Q is assigned a value of 0, and then we display the value of P, right? So if you have not seen this question, I will suggest that pause the video for some time and analyze this code and try to predict the answer to this question. You may run a Verilog simulation tool also to find the answer, but the problem is that it is not easy to infer the correct output using the Verilog simulation tool also. So let me explain why, right? So the short answer to this question is that in this code, there is a simulation race, right? So what is a race? We'll see. But since there is a simulation race, the output will depend on the order of processing Verilog constructs. And since it is dependent on the order of processing, different tools can give different results for this code. So if we just run one tool, it will produce some answer and we'll think that this is the correct output. But since there is a race, another tool can give another output and that output is also correct, right? Now in this situation, actually I ran the tool, a simulator that is iCarus, and it displayed the value of the variable or wire Q P as 0, right? After 5 time units, it displayed the value of P as 0. While I use another industry standard tool such as NC Verilog, and that produced an output 1. Now, which of these two outputs are correct? The answer is both are correct, meaning that from the tool perspective, both are correct because both output are legitimate as per the IEEE standards, right? So the problem is not in the tool. The problem is in the code itself, right? The code itself has a race condition and we should understand what is a race and we should avoid writing this type of code. Now to understand race in Verilog simulation, we should understand the mechanism of Verilog simulation, right? Now how does the simulator work, right? So whenever we apply stimulus to a net or a variable in our design, then it creates an event which is known as update event. For example, if we write a value a is equal to 1, right? So we are basically updating or we are assigning a value of a to 1, and that is the stimulus that we are applying, and the value of the net a will change to 1. Now if there is a statement written somewhere as assign b is equal to a, now since the a value of a has updated, the b which is dependent on a must be evaluated. So update event can trigger evaluation event, meaning that if a changes its value, then if then the value of b which is dependent on a should be evaluated and it needs to be updated also. So evaluation event on b will be created and the evaluation can further change value of the nets or signal and it can lead to a new update, right? So the value of b will be changing, right, in this case, And since B can further be on the RHS of some assignment, some other variable needs to be evaluated and then updated and so on. So the tool basically creates a sequence of update, evaluate, and this goes on until the end of the simulation time, right? Now, this is the mechanism of Verilog simulation, and in this update evaluate sequence, the order of time that we specify in the Verilog code or in the test bench, that is followed. Now let us look into the code that was given, right? So in this code, the simulation, or in when we start a simulation starts at 0 time slot. So in this case, at 0 time slot, first a stimulus q is equal to 1 is applied, right? So stimulus q is equal to 1 is applied at 0 time slot, and p is, because p depends on q, now p will be evaluated, right? So p is evaluated and it is updated to 1. So at the end of 0 time slot, q is equal to 1 and p is equal to 1. Then the time advances to the next time slot, right? So the next time slot is hash 5, right? So the fifth time slot. So then simulation moves to the 5 time slot or fifth time slot, and the stimulus is applied, q is equal to 0 at this point, right? Now q is being applied at time slot 5, right? So this stimulus q is equal to 0 will again require p to be evaluated and updated to 0. But now there is a problem. The problem is that when will this display statement be called? When will the next statement display will be called? Whether it will be called before updating p or after updating p. If it is called before updating p, then p will show a old value, right? Old value was 1, right? If it is called after evaluating or updating p, in that case the value shown by display will be 0, and the output will be dependent on the order of display being called in this case. Now which of these statements will be executed first, whether display or assign? So to decide that, what Verilog does is that it gives us a stratified event queue, right? Now let us look into stratified event queue to understand that within a time slot, which construct gets higher priority in evaluating, right? So this is what is known as stratified Verilog event queue. So this is stratified Verilog event queue. Now this is a conceptual model that explains how different Verilog constructs are simulated within a given time slot, meaning say at 5 time slot, which event will be evaluated first, next, and so on. So the events at a given simulation time is divided into 5 layers and processed top down, right? Meaning that the highest priority is the active events. Active events contain assign statement, blocking assignment, RHS of non-blocking assignment. Note that RHS is evaluated in the active event for a non-blocking assignment, and the then it goes to inactive events where 0 delay assignments are evaluated, and then it goes to the NBA update where the LHS of the non-blocking assignments are evaluated, and then monitor and monitor and strobe are evaluated and or executed, and then it moves to the next time slot, right? Now there is no priority among active events. So execution order among active events is arbitrary, meaning that if there are multiple events that is in the active event queue, that is assignment, blocking assignment, RHS of NBA, a non-blocking assignment, or display, all have the same priority as per Verilog standard. So the tool can execute or pick any one of them and execute in whatever order it wants, right? This is what is specified in IEEE standards, and simulation tools follow the same thing, right? So the execution order among active events is arbitrary. Thus, and this is a source of indeterminism in simulation of Verilog code. This leads to indeterminism, meaning that we cannot decide which one will be executed first and second. Now, why this kind of thing is introduced in the Verilog standard? The reason is that if we consider a circuit in which elements or if you consider a hardware, there will be multiple elements in the hardware, and all of them are executing in parallel, right? So we never know that if things are being executed in parallel, which will be executed first, or start the execution first, and so on. And this mechanism, or giving the same priority to all the events in the active event queue, is one of the ways which models the parallelism in the hardware. And this kind of parallelism is missing in the traditional programming languages. This is a feature which is of hardware description languages. Now, note that statements in a sequential block are executed as they appear in the blocking, as they appear in the block. For example, if you have an always block and we have statement 1, 2, 3, then they will always be executed in top-down manner as it is written in the code. There is no indeterminism in that. It is totally deterministic behavior. If statements are written in within a block, right? It can be initial block or within a always block. Then they are executed sequentially, one after the other, as per the IEEE standard. There is no indeterminism in this case. But if they are different blocks and they are put in the active queue, active event queue. For example, there is one always block, right? And there was one assignment, right? And there was another always block in the module, and it also had an blocking assignment. Now, which of them will be executed first? In this case, there is a indeterminism, meaning that if the codes are of different blocks, then they can be put in the active event queue in any order, and this creates indeterminism and race, right? So non-blocking assignment, that is this one, or the whenever non blocking assignment updates are made, it can trigger further events in the active event queue. So it is not that it is executed only in the top-down manner. When it reaches at this point, it can again set some active event queue, because some variable may be dependent on what was updated in non-blocking assignment, and because of that those events are created in active event queue, and therefore it will again, execution will go into the active event queue, and then it will go again in this order, right? It can be done multiple times. Now let us look into that, what does this mean for the example that I have shown, right? Now in this example, when q is equal to 0, event was there for at time slot 5, then an evaluate update event for p must be evaluate or update event must be made for p, right? This statement, and that is the assign statement. Now where is this assign statement? This is in active event queue, right? And then we have the display statement just after that, and that is also in active event queue, right? So there is no priority among active events in the stratified event queue, and therefore either the tool can continue and execute display. So after executing q is equal to 0, it can display this line, or this can execute this display line and show the value of p. In that case, p will shown the old value, that is 1. And the other tool may decide that it will update p first, because it is in the active event queue, and the tool can choose out of assign statement and display anyone to execute first. Another tool can pick assign statement first and it can execute, and in that case the new value of p will be shown, right? That is p is equal to 0, and hence the result of the display will be different in these two cases, and therefore there is a simulation race condition, right? Now let us formally look into what is the definition of the race condition in Verilog. So the Verilog language specification or IEEE standard defines which statements have guaranteed order of execution. For example, statements which are in the block in the sequential block, that is between begin and end, the statements those are executed as they appear in the code, and there is a guaranteed order of execution. And which statements have no guaranteed or indeterminate order of execution. For example, the statements which are there in the active event queue, there is no guaranteed order of execution, right? So this is what is defined in the Verilog standard. Now, what is a race? So when two or more statements that are scheduled to execute in the same simulation time and would give different results when the order of execution of the statements are changed as permitted by IEEE standard, then race condition is said to exist, right? So in the example shown, that was true because the output can be either p is equal to 0 or p is equal to 1, and it depends on the order of execution, and the order of execution can be anything as per defined by the IEEE standards, and therefore there is a race condition in this case. So race condition can occur many a times in simulation, right? And it takes a lot of effort for the designer to debug the race condition, fix it, and so on. Why we want to fix it? Because the behavior is tool dependent, and therefore the behavior that was assumed into simulation may be different what is there in synthesis, and therefore a design which was verified correctly in simulation may actually fail when it was synthesized, and we may have a bug which is hidden deep inside our design, and therefore we shouldn't have race condition in our design. They are difficult to debug, and uh, uh, there are some ways in which we can avoid race conditions in Verilog. So we can use some good coding practices which can help us avoid race conditions in Verilog. For example, there are some guidelines which can help avoid us race condition. For example, we should use non-blocking assignment for modeling sequential circuit and blocking assignment for modeling combinational logic, right, inside an always block. This is a guideline which is typically followed, and these guidelines are there to avoid the race condition. Then we should not mix blocking assignment and non-blocking assignment in the same always block, and we should not write to a variable in more than one always block, because if we do that, depending on which always block means being executed first, the results may vary, and therefore there may be a race condition. So we should try to write to a variable in only one always block, right? And there are tools or the rule checkers which helps us check whether whether these guidelines are being violated or not. If these are violated, then we should need to fix our design and the test benches, right? So if we follow these rules, then we can avoid facing problems later in the design flow. For example, there are tools such as Spyglass which can help you detect race conditions by, or help you avoid race condition by checking whether some rules which if violated will lead to race condition, those rules are whether followed in our design or not. Now, if you want to know more about the things that we discussed, you can look into this book, chapter 9.3.4, pages 158 to 59. And this you can join the Google group of this textbook, VLSI Design Flow, where we discuss these types of problem, and you can directly interact with me. To join this group, you can send an email or empty email to vlsidesignflow plus subscribe at googlegroups.com. Thank you very much.